I'm going to begin by motivating what's going on. What is the object that we're looking for, and how does it relate to some of the other things that we've talked about? So, first of all, think about V being a finite dimensional vector space, which is real or complex. We'll relax the finite dimensional, but the real and the complex will stick around. So we talked about how given a vector V, or a vector space V, we also have the notion of a dual vector, which is a vector in the vector space of linear transformations from V down to the field. And there's a little bit of asymmetry in this definition. So another way to think about this space is as the space of linear transformations from the field, which is a perfectly good one-dimensional vector space over F, to the vector space itself, V. Right? Sort of tautologically, every element in here is also a function. What function is that? It's the function that so as an element of the space of linear transformations from the field to the vector space, V is the function that sends a field element, say C, to C times the vector. That's a perfectly good linear transformation. And when we think about, say, matrices, right, we associate, in other words, we think about the vector space V is C to the n. Both of these types of vectors, vectors in the dual and vectors in V, have matrices, and those matrices are just the transpose of each other. Right? So like if V looks like this, V star looks like that. And since these are just matrices, I know how to multiply them. And if I multiply them, I get field element. Right. You can also think about this with these pictures. So V, I want to think about as a linear transformation that goes from the field to the vector space V. And an element of the dual, alpha, I want to think about as something which eats an element of the vector space V and spits out a field element. If I have an element of the V and an element of V dual, I can combine them to get a field element, alpha of V. Right? So in this case, it would be multiplying these. So we talked about how, for this reason, V is isomorphic to its double dual, canonically. That is, V is isomorphic to V star star, canonically. Canonically meaning that there's only one possible choice. V star star is the space of linear transformations from V dual to the field. That is, it eats a dual element and it spits out a field element. And so the canonical isomorphism here says for each V, I can get something in here by just saying V goes to evaluate the thing in here at V. Right? And that I don't have to make any basis choice for, or any other choices. But this isomorphism, for finite dimensional vector spaces, V and V star are isomorphic, but they're isomorphic in a way that requires a choice. And what we're going to understand today is what the minimum such choice is. Okay, what it means to make such a choice. So here's one situation in which we know how to do that, right? If I have V and I write it this way, so like if V is C3 and I have a vector V which is A, B, C, I know how to associate an element of V star to that, or I know a weighted element. Let's make this R3 for now. That will make it better. I know how to associate an element of the dual space to that. Well, I can pick this element. That's in the dual space. That's a pretty good definition for what V star might be. And then given these two things, I can combine them to get this. I could take V star of V, and that's A squared plus B squared plus C squared. Okay. Well, it didn't seem like I made any choice, right? So what was so somehow here, I was able to take a vector V and give you an element of V dual. So I somehow had to make a choice, if you believe me about this canonical isomorphism. So what's the choice that I made? It's kind of hidden. Well, let me ask it this way. Suppose V is a three-dimensional real vector space. Space of arrows in this room. Let's start from right here. That's sort of the same situation. So here's a vector. So what's the dual vector that I send that to? Well, we're getting, yeah, we're trying, one of the things we're trying to do is get the length. So the problem is there is a choice. There was a choice hidden, which is that if I think about this as it's not being V, this is just a three-dimensional real vector space. I chose a basis. I chose a basis for V. And when I chose a basis, that gave me enough information to decide how to construct an element of V star, which is just write the same elements, but in a row instead of a column. So it turns out, as that example shows, that a basis is a sufficient choice to determine an isomorphism V to V star. It's also a sufficient choice to answer the question, what is the length of something, right? To get length and to get a function G with two inputs, both of which lie in the vector space V and spits out a field element, and which will turn out to be linear in each element. So it's sufficient, but it's not necessary. That is, there's some weaker choice I can make that allows me to, for every vector, such as a vector in R3, identify another vector without choosing a basis. So that shouldn't be too surprising because I can measure the length of things in real space without picking a basis. Right? So there has to be some way that I can do that. Or another way of saying it is that no matter what basis I choose, there must be some way that I can have the same answer for the length of a vector in three-dimensional space. So let me say a couple of other ways what it is that this piece of data, what this piece of data should satisfy, or what the desiderata of it is, and then we'll say what that data exactly is that we need in order to make that smaller choice. So another way of saying it is that, okay, so I want to say that this data should, or this choice, should identify a V in V. It should give me an alpha sub V in V star. Right? It should give me some linear map from V to the field. Or equivalently, given two vectors, U and V, it should give me a way to combine them like this to get a field element. alpha sub u, whatever this map is, of V. That would be the field element. Right? Or in this picture, I take my V, I map my, I take V, I take my U, and I map it to alpha sub u, which is something in the other direction, and I can combine them to get a field element. Yet another way of saying that is that I can observe that this thing is going to be linear in both elements, or depending, let's say if everything is real, it's going to be linear in both elements, depending on my method of identifying them. So, if I have two linear transformations and I apply them to V, that's equal to alpha of V plus beta of V. So it should be additive in the first argument, whatever it does to this side. And it's also true that alpha of V plus V1 plus V2 is equal to alpha of V1 plus alpha of V2. Right? If alpha is a linear transformation. So we wanted something, and scalars work more or less similarly. So we want something that is as linear or as linear as possible in both sides. That's part of our desiderata. So we want a bilinear map. And there's a wrinkle to that, which I'll talk about in a second, but that's the idea. And so it turns out that this data, this choice, is called an inner product. So that is exactly what I need to be able to do all these things: compute length, send a vector to an element of a dual, and do that without necessarily choosing a basis. So what I'm claiming is that a basis defines an inner product, just a dot product, but not the other way around. An inner product doesn't necessarily define a basis. And that's why it's possible to talk about length in the real three-dimensional space, even though we don't have a given basis. Okay, so it does lots more beyond that abstract idea of how to combine things like this. And because we want to talk about length, let's work out a little bit more carefully how length works, so that we can make sure that whatever our definition of inner product is, it does what we want with respect to the idea of the length of a vector. So consider the blackboard as a two-dimensional vector space, and let's pick a basis of it that's a quote-unquote standard basis, 1, 0, and 0, 1. And let's consider some vector, call it x, in this blackboard. So x I can express as some coefficient x1 times this. Let's call this u and this v. These are our basis vectors. x2v, or more concisely, since this thing is isomorphic to R2, the vector space of pairs of variables, pairs of real variables, I can just write x as x1, x2, right? So using a theorem that's quite old now, Pythagorean theorem, we can find the length of x, right, just by this right triangle rule that you learned a long time ago. That is, the length of x, the norm of x, is the square root of the length in one direction plus the length in the other direction. If x is in R3, that would be square root of x1 squared plus x2 squared plus x3 squared. Okay, so we wanted something that was linear, as linear and possible in both arguments. So this doesn't look like a linear function. There's squares and square roots. So we have to change it around a little bit to get something that at least has the possibility of being linear in its arguments. And then we want this function of length to be where you plug in the same vector twice on both sides. So we could write it like this: x squared, the squared length of it, that gets rid of the square root, is x1 squared plus x2 squared, which is x1, x1 plus x2, x2. Okay, so that looks like something now that could have two inputs. two vectors as its input. And it just so happens that we plugged in x1, x1, or x1, x2, and x1, x2. Right? That was one goes there, and the other one goes there. So here, what we have is what's called a dot product, x dot y. X dot y is x1, y1 plus x2, y2. And we've just plugged in the same vector on either side of the dot product. So the basis, choosing a basis, defines a dot product. And this has what we want in terms of linearity, at least for, if you think about, we're in R2. And it's certainly true that if I have x plus y dot z, that's equal to x dot z plus y dot z. And similarly, x dot y plus z is equal to x dot y plus x dot z, regardless of the dimension. So the dot product, once we've chosen a basis, is an example. We can say that it's, at least for this real thing, it's bilinear, or linear in each argument. And we want to think about our inner product as something which is a data that solves this abstract question I was asking earlier, and also something which is an abstraction of this notion of dot product that allows us to measure length even without having a basis around. But before we do that, there are some issues that are created by thinking of it this way when we work with not real but complex vectors. What do those issues look like? Well, suppose I have x1, x2 complex vector, and I take x is this, and I take the dot product of x with itself in this sense. Well, what does that give me? That gives me x1 squared plus x2 squared. And I like to take the square root of that and call it the length. What's the problem with that? Well, what if I choose my x to be I, for example? What am I going to get as my squared length? I get, well, I squared plus I squared, minus 1 plus minus 1. So I'm going to get that the squared length is minus 2. Now, that's not a very good length, because that means our square root of that is going to be a complex number. Complex numbers make not very satisfying lengths, right? So we have to adjust our formula somehow so that doesn't happen. And we could do that using complex conjugation. So if you remember, if I have a complex number, I can always write it as a plus bi, with I the square root of negative 1, a and b both real. And it has a conjugate with a bar over the top, and that's just a minus bi. So we just change the sign of the coefficient of I. And then if I multiply the complex number and its conjugate, the cross terms cancel, and I get a squared plus b squared, which is a nice, since a and b are real, this is going to be non-negative. And this is called the square root of this number is perfectly well defined and is called its norm or complex modulus. If you think about the complex numbers as a complex plane with a real axis and an imaginary axis, this number here is just the length of the complex number as a vector. It's a linear combination of a real number and I times that, and the length of the vector is this number here. Okay, so with that trick, we can define a sensible norm which gives me positive or non-negative lengths on Cn. So if x is a vector in Cn, I can define the norm of x to be square root of, well, whatever the absolute value of x, the norm of x, the moduli of the individual complex number squared xn squared. And we're working with the squared norm. I get the sum I equals 1 to n of xi conjugate, because that's equal to that squared. Okay, so that means that this suggests that the adjustment we want to do is to define x dot I, or the inner product of x and y, with x and y and Cn. We want to define that by taking the conjugate of one of these, so that when I plug x in for both, I get a real number. So that would be sum I equals 1 up to n, xi, yi bar. Okay, so that fixes that problem. And now, if I plug in x twice, that gives me this number squared, length of x squared. Okay, so that's an example of a good choice of an inner product. And now let's lay out what the abstract definition will be. So you can think about this again as like something which answers all these questions about isomorphisms, or something which is an abstract version of the dot product. Okay. Let V be a vector space over F, an inner product on V is a function that takes an ordered pair of vectors in V to a field element. And the name of that field element is bracket UV, the inner product of U and V. And we have some axioms we'd like to satisfy. The axioms are quantified over for all U, V, W in V, and for all field elements A and F. And here are the axioms we would like. First is called positivity. This was this problem that we had to go through this rigmarole to correct. That's that we'd like the inner product of any vector with itself to be non-negative, so that we can view its square root as a length. We'd like definiteness, which means that if I take the inner product of a vector with itself and I get 0, that happens if and only if the vector itself is the 0 vector. That's 0 in the field. That's always a field element. We have a couple of other things. We want to do this kind of linearity, or as close as we can get to linearity. We're going to be pretty close to linearity except for this issue. So additivity is fine. That is, we want U plus V, inner product with W, to equal UW plus inner product with V and W. And we want homogeneity. So right now we're just talking about the first slot, right? So in this first slot, it's additive, and it respects scalar multiplication as well. AVW equals A VW. And so these together say that this inner product function is linear in its first slot. Right? Linear in its first slot, but it's not quite linear in the second. So the last one is conjugate symmetry. And so this you can think of as sort of what's going on here. I'll explain how they connect in a second. And that's that the inner product of V and W is equal to the conjugate of their swap of the inner product of W and V. The conjugate of the inner product of W and V. Now, if we're in the real case, that doesn't do anything. So that's why I liked the real case as an example. We don't have to worry about that as much. Okay. So this means that in the second slot, that's the end of the definition. In the second slot, we can see how much of these properties are preserved. So these things are symmetric, but these are not. So the inner product of u and v plus w is equal to, by conjugate symmetry, the inner product of v plus w and u conjugate, which by additivity is equal to the inner product of v and u plus the inner product of w and u. I conjugate the whole thing, but since conjugation commutes with addition, I can just conjugate each of those separately. But then I switch them back to get rid of the conjugate, and that's uv plus uw. Okay, so that means that it's additive also. So it's also additive in the second slot. But if I do the other thing, if I do scalar multiplication in the second slot, I can swap them at the cost of conjugation, and then I pull out the c, but it's been conjugated, and I can't get rid of that. C bar, and then I can swap them again at the cost of conjugation. That tells me that in the second coordinate, it's additive, but it's not quite linear. So with scalar multiplication, when I pull out the scalar, it gets conjugated. So it's conjugate linear, those two properties combined in the second slot. Another word for this is sesquilinear, a function which is linear in the first and conjugate linear in the second. You should also note that if I take the inner product of the zero vector with anything, I get the zero field element by scalar multiplication. Multiply anything by zero, it's going to have to be zero when I pull it out, no matter which side I do that. OK, so that's our definition of inner product and some of the immediate consequences of it, which sometimes get packed into the definition, depending on your source. And a vector space equipped with an inner product is called an inner product space. Complex or real vector space V, vector space V with an inner product, sesquilinear inner product, but that's the only kind we have. Okay, so let's look at a couple of examples. First example is the one we've already been talking about. That is a dot product. So let's say our vector space is Rn or Cn. And we want to take the inner product of two vectors. We can do that by taking their dot product, except that we have to do this conjugation thing in the second factor for things to be sensical in the complex case. So that's an example of what's called a Euclidean inner product. Of course, the conjugate doesn't do anything if we're in the real vector space case. So that seems like the only choice, but there's actually a lot of other choices of inner product. So for example, if we let C1 up to Cn be positive real numbers, then I can plug the C's in here, and I can define the inner product of x and y to be the sum from I equals 1 up to n ci xi yi bar. And you can check that that satisfies all the axioms. So that's also a perfectly good inner product, and so there's at least infinitely many of them. You could think about this as being a matrix multiplication. That is, it's I have x written out this way, and then we have a matrix C, and then we have y written this way. Let's say everything is real, for example. Right. Well, that's without the conjugation, but let's conjugate this one. Okay. And what we're saying is that this matrix C, if we're in this situation, the matrix C is diagonal, with C1 up to Cn with all these C's positive. But it's certainly, let's put this conjugates on the inside, that's a little clearer. But it's not even required that this matrix be diagonal. So there are other choice of matrices which are not diagonal, which still give perfectly valid inner products, but there's some conditions on them. So not every matrix is allowed. It needs to satisfy all the axioms, and the last three axioms don't bind, so they're not going to affect our choice of matrix, but the first two axioms are very much going to affect the choice of matrix we're allowed to put in there. And the condition that C must have is that its C is positive definite. So it has to, only some matrices allow those first two axioms to be satisfied, writing the inner product that way. That is, if V transpose C, the conjugate has to be greater than 0 if V is non-zero. And that imposes some restrictions on this matrix C. And this is one way of describing those restrictions. You can see there's an inequality. So it's actually like a cone of matrices. And we will need to find other ways of characterizing this as we go on. You can, for example, characterize this property in terms of eigenvalues. You can talk about the eigenvalues of C and do that. Okay, so let's do a couple of other examples. Here's an infinite dimension one. Let this be the vector space, infinite dimensional vector space of complex polynomials in one variable. Then for two polynomials in C of x, there's an inner product, which is the integral P of x, Q of x bar dx. In fact, that would work for any other continuous functions defined on the interval 0, 1, which works in particular for polynomials. And so let's see that length was one of the motivating examples or things that we desired from an inner product. And let's make sure that we define what it means to do that. So every inner product we get defines a norm or a length function, which is just the square root of the inner product of the vector with itself. And note that the axioms for the inner product tell us that the only way I can get something of 0 length is if V is already 0. And if we think about what happens when we scale, so if I take the squared norm and I multiply by a field element A, that's equal to AV. So we'll have lots of questions now about inner products. And one of the main things that you'll do to solve things is you see a norm expression. Very often what you do is expand it into a seemingly pointless inner product expansion, then work with these guys, flipping them and the various axioms in order to prove what you're trying to prove. So if you see something, you're trying to prove something about a norm, almost always what you need to do is expand it and then manipulate that using linearity and the other properties. So this is equal to pulling out the first A by homogeneity. And then the second one I can pull out, but I have to take the conjugate, A bar VV. So that tells me that let's start over here. That tells me that the norm of AV squared is the modulus of A squared, and or the norm of A squared, norm of V squared. And if I take the square root, I end up multiplying just by the modulus of A. So one of the many things we can do with inner products besides tell length is that we can develop a notion of what it means for two vectors to be perpendicular to each other, to be orthogonal. The definition is that two vectors, u and v, in an inner product space are called orthogonal if their inner product is 0. And so in particular for that definition tells you that 0 is orthogonal to everything including itself, which is a little odd, but one edge case to keep in mind. And when we have orthogonal vectors, we can do the thing, we can compute lengths like we did a second ago using the Pythagorean theorem. That is, if this is the Pythagorean theorem in inner product language, if I have two vectors which are orthogonal in V, and if I say they're orthogonal in V, that means that there has to be an inner product on V, so V is an inner product space, then the norm of u plus v squared is the norm of u squared plus the norm of v squared. That's Pythagoras' theorem. And the proof, I take u plus v squared. As I said, when you try to prove something about a norm, the first thing you should do is expand it. U plus v. Now let's use additivity. This breaks up into 4 terms: UU, UV, VU, and VV. Sorry, these are pluses. Okay, it's the sum of those things. But UV and VU are both 0 because U and V are orthogonal. And then so that these are the norm of U squared plus the norm of V squared. So that's what makes that tick.